We'll begin by talking about the purpose of the charge tape lab, which is to display the electric fields exerted by two charged objects and their corresponding forces that the objects exert on each other. By determining the distance at which the electric force on the upper piece of tape counteracted the force of gravity on that upper piece of tape, we sought to determine the charge on each piece of tape after friction was introduced by pulling the two pieces of tape apart. For this lab, we used two pieces of Scotch tape to act as the charged objects, a meter stick to measure the distance between the charged objects once the upper piece of tape began to float, and two stands to suspend the upper piece of tape. We charged two pieces of tape by sticking them to another piece of tape and rapidly unsticking them, as friction can introduce charge to a previously uncharged object. We then suspended the longer of the two pieces of tape and moved the other charged piece of tape slowly towards the other suspended piece of tape until the suspended piece of tape moved upwards. We then measured the distance between the two pieces of tape when the suspended piece of tape began to float. The system was the tape suspended in the air, and its surroundings were the other piece of charged tape and the forces acting upon it. The results that we calculated were as follows. We found that the charge on each piece of tape was about 6.67 times 10 to the negative 9th coulombs, and each tape lost about 4.17 times 10 to the 10th electrons. Within this experiment, we noticed two fundamental principles. Starting with Newton's second law, that force is equal to the derivative of its momentum with respect to its velocity, aka F equals ma. We used this to determine the force of gravity counteracting the electric force on the upper piece of tape. Moving to the electric side, the second fundamental principle we used in this experiment was Coulomb's law, which describes the interactions of repulsion and attraction between two charged particles. And through this, we were able to calculate the force acting on the upper piece of tape from the lower piece of tape's electric charge. In order to make our experiment feasible, we made a couple of assumptions, mainly that tapes are negatively charged and equivalent in magnitude of charge. Any additional forces besides gravity and the electric force from the lower tape were ignored, and that pieces of tape were treated as point charges rather than a collection of point charges. Additionally, we acknowledge that there could be some potential errors in our experiment, stemming from treating pieces of tape as a point charge, which was not fully representative of the distribution of charges, errors in handling that could cause the grounding effect on both the lower and upper pieces of charged tape, and finally, inaccuracies in the measurement, which could inaccurately reflect the true distance at which upper piece of tape began to move upwards, which could affect the calculation of magnitude of charges. For our calculations, we started by calculating the force of gravity acting on the upper piece of tape. First, finding the length of the tape, then using that in combination with the density to find the mass, and then using the mass to calculate the gravitational force acting on the upper piece of tape. We then use this gravitational force to set it equal to the electric force acting on the upper tape using the distance figure that we measured at 0.04 meters. We then use the same magnitude of the gravitational force to calculate the electric charge of each tape using the formula displayed below, and got 6.67 times 10 to the negative 9th coulombs. We then calculated the electrons lost by taking the ratio of the charge compared to what the magnitude, and then dividing that by what the magnitude would be had all the electrons been present, and found that we lost 4.17 times 10 to the 10th electrons. Using known constants and the measured variables from the experiment, as well as treating tape as point charges, we're able to calculate the force of gravity on the upper tape and use this to find the electric force from the lower tape. We were then able to use this electric force to find the charges of both tapes and then how many electrons we lost throughout the experiment. We then created direction vectors for each observation point, then created a function to calculate electric field, and used this to calculate the electric field observed at the upper tape from the lower tape. Then we used this electric field to calculate the force from the lower on the upper piece of tape. Ending with some additional questions, if the electrons had positive charges and protons had negative charges, While the direction of the field would change, the results would remain the same, as both tapes would have electrons and repel each other. Finally, avoiding contact with the charged side of the tape is important to avoid the grounding effect, which could neutralize the piece of tape and diminish the effects of its electric field.